say you have a spring attached to the mass and this moves on a plane that's not frictionless, it has a linear drag. So if it doesn't have any like applied force on it, what's going to be the equation of motion for it? The inertial frame. So yeah, it's a one-dimensional system, so we can use equal without any vector signs. So we can write mx double dot x is like displacement from the equilibrium x, when it's displaced from this the equilibrium between this straight it and like a space from this point and release it. So oscillate back and forth, and this is the equilibrium, like this is the displacement from the equilibrium. Right? So the force should be, so what are the forces should be acting on this object?
kx dx, dx
minus kx dx dot.
One is negative kx, right?
Yeah.
Because it should be opposing the like the displacement. So and another is negative dx dot. So it will be try to stop like the drag force will try to like reduce down the velocity and make it stop. So yeah, it should be negative as well. So these are the things that we have to consider, right? Yeah. So it has a simple homogeneous linear differential equation that looks like this. So do you know how to solve it? This kind of differential equations?
No, I think we can.
It's exponential dk sinusoid.
Yeah.
Okay, so yeah, we can like substitute a trial function here and see what happens, right? So before doing that, we actually simplify the notation. We simplify our notations a little bit. So divide everything by m. So we get x double dot plus e by m x dot plus k by m x goes to 0.
Yeah.
So let's define several things. One is gamma. That let's define gamma equal to poison. It's called the damping factor. And let's define another thing that is root k over m. So this is basically the frequency of undamped oscillation, right?
Yeah.
So we know how to solve it. So let's do the trial function. Like say our trial is x equals to some constant e to the power some another constant p, which is unknown, multiplied by t. Substitute it, you get p squared a e to the power pt, because it's
square plus
yeah
2bp plus omega square
v by m. So or gamma you could write. So for the beginning, let's write just v by m. I'll use this in the last step. Okay, so then you have v by m into p a e to the power pt plus k by m into a e to the power pt, right? Is equals to 0. So a e to the power pt cannot be 0 identically. Yeah, that's also a solution, but if it is identically 0, then it's a trivial solution. We are not interested in that. So we say that our a e to the power pt is not 0. So we can factor this out and we get a e to the power pt a e to the power pt multiplied by p square plus b by m multiplied by p plus k by m equals to 0. So this thing cannot be 0. So this thing has to be 0, right?
Yeah.
P square plus b over m p plus k by m. It has to be
I
0.
think we can put gamma and omega square here.
Yeah, we can do, like I'm going to do that in the last step, like after solving the quadratic equation. So in terms of p, we have a quadratic equation and we know how to solve it. So what's the solution? So p equals to, it has two possible solutions.
Minus b by m.
Minus
b by
b by m
b by m plus minus
square
root
root of
over yeah
b by m whole squared
minus 4 k
minus 4
k by m.
k over m. Is that all?
Yeah.
So we take this half inside of that, like this half factor inside of there. So we get negative b by twice m plus minus square root of. So when you take 2 inside of this square, you get 1 over 4 basically. So we can write b over 2m whole square, right? Minus, yeah, 4 k by m. You can take a square root over here and put square root there.
I think we can ignore the 4 because it will be divided by the 2 we actually.
Oh, okay, yeah. So it shouldn't be here anymore because
Yeah.
we have a 4 inside of it here. Now that's all, right? So it has a specific form, so that's why we define some damping factor and all that. We can use that here. So using that definition, we get negative gamma plus minus square root of gamma squared minus omega squared, right? This is the two solutions for T.
Yeah.
So substituting back, we get one possible solution is x equals to some unknown age e to the power this whole thing that with just one part, like probably the positive part. So negative gamma plus square root of gamma squared minus omega squared multiplied by 2. This is one possible solution. A is 1. And another possible solution is 2 is some another constant e to the power negative gamma minus square root of gamma squared minus omega squared multiplied by 2. So these two are possible general solutions. So we can add those and find another solution. So in any linear combination of those two is a general is a solution as well. So our general solution is x equals to some unknown e to the power negative gamma plus square root of gamma square minus omega square of 2 plus b e to the power negative gamma minus square root of gamma square minus omega square. So if you factor e to the power negative gamma t out, then you get e to the power negative gamma t a e to the power square root gamma square minus omega square is 2 plus e to the power negative square root of gamma square minus omega square. So this is our general solution to a damped harmonic oscillator, right? So generic one. Absolute general and generic solution. So we haven't used any.
Actually, can we say it is a generalized solution because it depends on the relation between gamma and omega, where gamma and omega is equal. The solution we actually get is not can't be derived from this.
There is a reason why we call it a general solution. So to have a general solution, you need sufficient amount of constants that you're supposed to get.
Yes, and
And
Of course, this relation does not hamper this because sometimes the power of the exponential might be imaginary, but it's not a problem.
yeah, that's not a problem as well. So there is a problematic case actually when gamma equals to omega. That's a problematic case because you do not actually uniquely like
that solution is not actually can be derived from this one.
Actually that can be derived from this one as well.
Okay.
So by taking a specific limit.
Okay.
Okay. So so when gamma equals to is greater than omega, that's not a problematic case, right? So we call it over situation. Overdamped situation. So then this thing is some positive constant. This thing is also a positive constant, but with a negative sign. So overall, it's a negative, right?
Yeah.
Okay. So in that case, we have like purely exponential solutions. There are a lot of physics going on here. I'm trying to skip all of those. We can say, okay, effectively the motion would be like this because it has a to the power negative gamma factor. So you have to add this gamma, like you have to subtract gamma from this and that. So you'll end up with having like this term basically negative gamma plus square root of gamma square minus omega square. Now let's analyze. So gamma is greater than omega. So this thing is positive. The inside of that square root is positive. So square root of some positive thing is defined as positive. But question is this part is greater than that one?
No.
It has to be smaller because
we subtracted omega square from.
Yeah, you have already subtracted omega square from that gamma square. Yeah. So this is smaller, this is bigger. So effectively, this will be something less than 0, right?
Yeah.
Overall, this will be negative. Also, for the another one, gamma, negative square root of gamma minus omega square, that would be also less than 0. But this one would be smaller than the other one, right? Yeah. So this is the smaller one, this is the bigger one. So as it is negative exponent, so actually you can neglect that part because the other one would be the dominating part. So the effective behavior would be like this, e to the power negative this thing. So that's what I have drawn. Like the long-term behavior would be this. When is being, then this term would effectively die out, and this term would be the like e to the power, like this term would be the dominant. So this is what we call overdamped. So actually, it's a slowly decaying situation because it's not that heavily decaying because the decay factor is not just gamma, like it's negative gamma plus square root of gamma square minus omega square, which is actually small, but not as small as just negative, right? So now we could have another situation when omega, actually gamma is less than omega. I want to write this. Gamma is less than omega. So in that case, this square, gamma square minus omega square, it will be less than 0, right?
Yeah.
But omega square minus gamma square would be
greater than 0.
Obviously. So we can actually factor out one minus sign from here in that case. So I'm just kind of reviewing things that you already know. So I'm not worrying much that I have to explain everything. So here a e to the power. So you have factored out one minus sign from there, like minus sign from this term. So you get e to the power when you take like square root of -1, that is defined as I. So e to the power I square root of omega square minus gamma square t plus b e to the power minus I, and the same thing, like omega square minus gamma square, right? And we all know that these two terms can be combined as like x is real. Number one, x is real. So if x is real, then if you take x star, that means if you complex conjugate it, the result has to be equal to x as well, right?
Yeah.
So if you take x star, what do you get? You get e to the power negative gamma t. Then you get a star, because a could be in principal complex.
Yeah.
A star e to the power negative I square root of omega square minus gamma square into t plus b star e to the power I square root of omega square minus gamma square into t. So, and as x is real, this has to be equal to x. So what do we get? We get a star is basically nothing but this thing and this thing are same. So this thing has to be equal to b, like a star has to be equal to b, and b star has to be equal to a. Right?
Yeah.
So there is a strong condition between these two. So using that condition, we can convert these exponential things, complex exponential things, into sinusoidal ones, right?
Yeah.
So let's say our a equals to small a plus ib, and then a star, which is basically b, would be a minus ib. So substitute those things over there, like over here. So our x would be e to the power negative gamma t, then a plus ib, e to the power I square root of omega square minus gamma square t. Can I write it as like omega prime or something? Like it's hard to write it.
Yeah.
We define square root of omega square minus gamma square equals to let's say capital omega. So if we define like that, then we have this. In this expression, like this gamma, this t, this a, b.
I think you should write a and b in polar form. It will make it way easier.
No. It's already in the form that I want. It's already in the form that I want.
Yeah.
I have a question.
So just give me a moment, then ask the question. So okay, so just we can add like the real parts, not just like we can factor out the a, and we can have like e to the power I omega t plus e to the power minus I omega t. This is one thing, and then plus if we factor out b, we have actually if we factor out ib, we have e to the power I omega t minus e to the power minus I omega t. So using the relationship between the complex exponential and sinusoidal, we know that cosine omega t equals to half of e to the power I omega t plus e to the power minus I omega t. Right?
Yeah.
So you multiply this thing by a 2 and divide this thing by a 2. Right? Do the same trick over there as well. So we know sine omega t equals to 1 over twice I e to the power I omega t minus e to the power minus I omega t. So what you need to do is like divide this thing by twice I and multiply the whole thing by a twice I, which would give you like negative I square means minus 1 and then this, right?
It will be plus finally because
Did I make a mistake?
Yeah. Okay. Wait. No, no, it's all right. Okay, it's all right.
I think it's fine.
Yeah.
So now we can write as e to the power negative gamma t. Let's say twice a equals to some c. Like let's define twice a equals to c. So we can write c cosine omega t, and let's say negative 2b equals to some d. So d e to the power, sorry, not e, sine omega t. So this is our solution when we call it under damped situation. So in the under damped case, we have a solution like this. So the envelope would be like e to the power minus gamma t, and inside of that envelope, the actual real motion would happen, like they oscillate and die out. So this is the trivial case we see in every oscillation in real life. Okay, so someone had a question.
Yes. Why we considered the value of x and the complex conjugate of x to be same?
Oh, because the x is real, like the distance, it cannot be imaginary, right? It cannot be complex. How can a distance can be complex?
No.
Any physical quantity has to be real in physics.
If
The
we
imaginary
go in,
mathematical artifact that shouldn't affect physics.
okay, it is why we considered x prime and x to be same.
X prime to be same? No. X star and x to be same. Like x has to be real. So for any real number, complex conjugate of it, like x star, has to be equal to itself, right?
Okay.
So
Okay.
2 star equals to 2.
Because the complex coefficient is 0, basically.
Yeah, because its imaginary part is 0.
Oh.
So for any, remember this thing, for any physical quantity, it has to be real. You can use a mathematical artifact for a while, but when you do the actual thing, that has to be real, no matter what. Okay. The final situation, that's a little bit complicated because, as I said, you have to take a specific limit to like consider that one. So actually, I'm not going into that detail. So I'll just do the simpler one. So let's consider the case when omega equals to gamma. So when omega equals to gamma, then we can write our differential equation was like x double dot plus twice gamma x dot plus omega squared equals to 0, right? That was our differential equation. So let's substitute this gamma by omega, because in this case those are same.
Yeah.
So if you substitute like a e to the power some pt, this is going to be a solution we already know, and we can find a solution for p.
Yeah, omega equal to p.
Yeah, omega equal to p. That would be the case, right? But my claim is some b t e to the power pt is also solution. Let's check. Let's substitute and check. If you substitute this thing, if you substitute this thing, what do we get? So now it's okay. So it omega square x equals to omega square b t e to the power pt, and then twice omega h dot. So twice omega multiplied by h dot. Now you have to take product rule. So b e to the power pt plus bt p e to the power pt.
Yeah.
Okay, then we have like we need the x double dot. X double dot would be like differentiate this thing again. So we get dp e to the power pt plus b p e to the power pt plus bt p square e to the power pt. Now add all those things and factor out bt e to the power pt. So if I factor out bt e to the power pt, actually I want to factor out like e to the power pt, not just b e to the power pt. So if I factor out b e to the power pt, I get omega square t plus twice omega plus twice omega t p plus p plus actually twice p plus tp square, right?
Yeah.
Is that correct? Like, did I make a mistake somewhere? Just check it if it is okay. So from one solution, we already know that P is a solution to the differential equation. That means P equals to omega. That was one. So let's substitute here. We want it to be 0. That's what we are trying to show. So if we substitute, we get b to the power omega t. Then omega square t plus twice omega plus twice omega square t plus twice omega plus t omega squared. This is what we get. So what we can factor out from here?
T.
T plus 1, I believe, right? T
Yeah.
plus no, one plus t. So let's see what we can factor out. So we can factor out how many terms? We have 5 terms actually. So let's factor out omega first, then see what happens. It's omega t plus 2 plus 2 omega t plus actually I should simplify first.
Yeah, it's 4 omega t is omega square t plus 4 omega.
4
Omega square t.
plus 4 omega.
Yeah.
Is that all?
It's all right.
Okay. Then we have b e to the power omega t, and if we factor out 4 omega as well, we get omega t plus 1, right?
Yeah. But that's not expected, I think.
No, 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 no.
We
Problem is like I'm trying to show that this thing is zero automatically.
yeah, but
So, yeah. And then made a mistake somewhere while differentiating this thing. Oh, actually, I have to consider one more thing. Why there is a T over there? There shouldn't be any T to begin with.
but why we could consider omega square t plus 2 omega tp plus tpa square as 0.
Yeah, that's what I was trying to use. Like we need to use like omega square plus
plus
plus 2
plus 2 omega p plus p square.
Omega. It's not omega p. Like it's omega t, right? Like 2 omega t. No.
If we factor out t, then omega square plus 2 omega p plus p square equal to 0.
Okay. Let's do it again. Sorry. So if we factor out t, that's what you are trying to say.
Yeah.
Omega square plus 2 omega.
Yeah. Plus p plus 2 omega p plus p square equal to 0.
Which term you are trying to consider? This one or this one?
This one 2 omega t p. It will be just 2 omega p.
Oh, actually you are trying to.
Then that will be 0 actually.
So what we use, like if I factor out t first, then omega square plus 2 omega p plus p square. Yeah, this thing is actually 0, right? Actually,
Yeah.
I made a mistake. Is the solution is not omega equals to p, like p equals to negative omega, right? That's
Yeah. P
That's
equal
what
to
I made a mistake.
negative omega.
So, this is the mistake I made. So this is the solution actually. So yeah. Okay. So substitute like omega p equals to negative omega over there. So that's the solution of the other one. So yeah, that's the mistake. So it should be this instead of positive. So omega squared t plus twice omega plus 2 omega, which should be negative 2 omega square t plus minus 2 omega minus this would be plus t omega squared, right? So now it becomes 0. Yeah, this is the mistake I made. Sorry, you should have checked it earlier. Like p should like omega is the gamma, and for p we get p equals to negative gamma, not positive one. So that's the mistake. Okay. So we have found our second solution. That is bt e to the power pt structure, where p is equals to negative gamma. So one solution is x equals to, from previous part, like you can check it. So that is a e to the power negative omega t or gamma t, actually I should write. And another is x2 equals to some b t e to the power negative gamma t. So if you combine, you get your general solution as like e to the power negative gamma t a plus bt. So this is the case for critically damped system. So for critically damped system, it might look like a overdamped system, but the decaying factor is the maximum here. So this is the fastest decaying phase. So these are the three possible solutions we already knew from our first year mechanics, probably freshman level mechanics. But now the new thing, what happens if we add a driving force? What happens if we try like this system? This is the thing I'm trying to teach you here. So there are many ways to solve it, but you'll learn the green function over here, the procedure of green function. So probably you have like an applied force like electric field. You're applying an electric field, and this is a charge system. So this could be one possibility. Another is like you could pull it using a string. So the differential equation is now is mx double dot plus bx dot plus kx. Instead of being 0, this is equals to some force applied to it.
If
T could be a function of time in principle. If it is a constant thing, then that's not a problem. That would shift the origin. But if f is a function of time, then that's a problem. You have to deal with it.
yeah,
So any idea how to solve this kind of systems?
using
Laplace.
Green's function by considering at first by considering an impulse like Dirac delta, and then we can use Green function to.
One possibility is using Dirac delta, like using procedure. One procedure is like using Fourier transform.
Yeah.
The common procedure.
Yeah.
Another is using like direct integration. That's also interesting procedure. So there are a lot of ways you can produce the same result. But here we are trying to learn one or two. The first one I want to teach is the Laplace transform procedure. Basically, that uses the Dirac delta. That's the use of Green function method. And another is differential, because those two are the most interesting thing and worth learning, because we'll use those kind of procedure later. So this is our differential equation, and you have to always supply some initial data, right? Say you provide your initial data as x naught, like x at t naught equals to x naught, and x dot at t naught, that means velocity at t naught, that's your v naught. These are the initial condition you provide. So question is, how do you solve it? How do you solve this this differential equation and find something in this way? First of all, we can simplify the initial condition itself. We can reparameterize our time, right? Like we consider the initial time, like t naught, to be our 0 time, like t equals to 0 time, right? So that would simplify the system. So this is still pretty much general.
Well, then Laplace transform.
Okay, Laplace transformation. So do you know your f of t? Can you perform a Laplace transformation on f of t?
Well, we can assume it is f of capital F of s, something like that. Then use this if we know the f, like it can be step function or anything.
So okay, so first we have to change our differential equation to a specific one. We call it the differential equation for the green function, actually. So, or the impulse function. It's a different differential equation we're talking about now. So that different differential equation, say it has the form is actually no. I should write using the original form. So let's say it's fine because I'm not going to use it here. So x prime dot plus kx prime equals to, instead of giving a function like that is distributed over there, you actually give a delta function. So that is this.
Impulse response.
You give it an
impulse response.
Yeah. Actually, response is this one. Response to impulse is this one.
Yeah.
This thing is impulse. Why?
Yeah.
Actually changing or differential equation? There is a reason. Reason is, if you have your f of t, you can always represent your f of t like this: negative infinity up to positive infinity of t prime, delta of t minus t prime, dt prime. So the goal is, what happens instead of giving a general f of t, what happens when you provide a click on it, right? So what happens when you hit this object by a bat, but for a really short moment. So you analyze the situation and use that result, that specific result, to find the result of the general solution, of the general differential equation you want, right?
Yeah.
So let's say that this differential equation has a solution x prime of t bar t prime. There is a reason we call it as a function of t and t prime, because when you are applying at some t prime, so changing t prime would change your x prime as well. So that's why let's call it g t prime. So our g t prime actually satisfies this differential equation, that is m g t prime double dot plus b g t prime dot plus a g t prime equals to delta of t minus t prime, right? So first analyze one property, that is g is symmetric. That means g of t prime
equal
equals
to
to g
t prime t.
Yeah, how? Because our delta function,
Because delta function is symmetric.
yes, it's symmetric, defined as this thing. Oh, wait a moment. So I'm assuming everyone knows about delta function. Do I need to explain it to anyone? I'm sorry for that, actually, I didn't notice. Do I need to explain delta function to anyone?
Yeah, I think so, if you can.
Okay. So you should have spoken out, like define delta function first. So delta function is defined as delta at t minus t prime. This thing is defined as it's infinity when t equals to t prime and it's zero otherwise. So it's basically a peak at like high peak like this. If you try to plot delta function, then at this point it has a very high value, otherwise it's...
I think the integration of delta function
Okay,
is the main definition.
Wait. Just a moment. I know that I have to say that.
Yeah.
Don't worry. Okay, so this is one thing. And also you need to, like, not all infinities are same. So if you multiply by the same infinity by a number, it's again infinity, but those infinity are ones bigger than another. So that's we have to take care of. So how? So there is another property we have to impose on delta function, that is delta of t minus t prime. If you integrate over t prime from the limit a to b, it gives you two things. 1 or 0. 1 when t prime it strictly lies between a to b and it's otherwise. 0 is otherwise. Okay. Sorry. A mistake actually. Actually, I meant like integration of t. So t prime equals yeah. T lies between these two things. Yeah, now it's correct. If t prime lies between a to b, then it's 1, otherwise it's 0. So it means delta function doesn't only have an amplitude infinity at that t prime point and other 0, otherwise 0, but it also has another property that it has an area exactly equals to 1. So you can think of it as an approximation to a Gaussian curve or like that. So you can consider like at t prime point you have sequence of functions. So first you start with a unit area and this is say it's t prime, and you start from the like this width is 1, also the height is 1. You can start with this, and then you make it thinner, like width is now half but height is 2, and then also thinner and like longer like that, and by doing successively you get your delta. That's what we mean by our delta. Okay, so it has an area 1 and it gives you infinity at that at one specific point, and otherwise it gives you 0. So mathematically speaking, mathematicians own call it a function. They call it a
State distribution.
Yeah. So, but to physicists, it's a well-defined function, and we know how to deal this kind of. So, yeah, it's physicist math, so we need not to worry that much. Okay, but there are more formal way to like escape delta function, but I'm not going to go into detail. And there are more there are different representation of delta function. That's what I'm not going to talk about today. I just want you to know just these two properties.
Right, there is one important property. If we integrate f of t times delta function dt, it will give just f of t naught t prime.
Yeah, so that's an outcome of this these two properties. So like these two defining properties. So yeah, if we want to introduce it for the first time, it's better to introduce like this. Say we have a function f of t prime, and you actually f of t, let's say f of t, and you multiply it by delta of t minus t prime and integrate over say some limit a up to b, where f of t could be defined outside of this limit, but it need to be defined at least inside of this limit. Like if f of t has to be defined over t equals to a to t equals to b. So in that case, we get f of t prime over that limit. Why? Because your delta function, it has an infinite value only at t prime. So we can write this integration as everywhere it's 0. So we do not care about the other point. So for other point, it becomes 0. Like we can split this integral a up to t prime minus epsilon. Epsilon is really small quantity. F of t delta of t minus t prime dt plus integration t prime minus epsilon up to t prime plus epsilon f of t into delta of t minus t prime dt.
Is it like a Cauchy principal value?
No. Cauchy's principal integral is something else that has to do with integrals. Actually, we need not to worry about that thing as well. Okay. So as we can see, like t prime actually it falls outside of this limit a up to t minus epsilon, because if we draw the number line, here is our a, and probably here is our t, and minus epsilon, so t prime minus epsilon, t prime plus epsilon. So in this limit, like t prime is outside of this limit and outside of this limit. So for this integration and this integration, we get 0, exactly 0, right? So we have to take care about the other one. So also we are applying a limit epsilon tends to 0. That's true as well. So limit epsilon tends to 0, integration t prime minus epsilon up to t prime plus epsilon, which means we're actually talking about integration over this region only. But we are successively we are trying to squeeze the limit as well, as we have applied limit epsilon to 0. So f of t delta of t minus t prime dt, right? So as this epsilon is really small quantity, and over that, like epsilon tends to 0. So what is the value of f of t at t prime plus epsilon, and what is the value of t prime f of t at t prime minus epsilon? That means I'm talking about just evaluate two things. Limit epsilon tends to 0, f of t at t prime plus epsilon. What's that?
F of t prime.
This is f of t prime. Also, what about the lower one? Limit epsilon tends to 0.
It will also give f of t prime.
It's again f of t prime, right?
Yeah.
So as this epsilon is really small, over this range, f of t remain mostly same, which is f of t prime, right?
Yeah.
So we can take this thing out of the integration, and we can write f of t prime multiplied by we have that limit applied epsilon, t prime minus epsilon, t prime plus epsilon, delta of t minus t prime dt prime. So what's the result of this integration now?
Just one f of t prime.
One. So we end up with having f of t prime. So we got our final thing, that is integration a up to b f of t delta of t minus t prime dt prime dt. This gives you f of t prime, or vice versa. So if you integrate over like prime, and if you have f of t prime, then you get f of t.
So f of t has to be c0 at near in the neighborhood of t prime.
Sorry.
F of t. F of t has to be continuous in the neighborhood of t prime, or c0 basically.
Yes, it has to be well behaved. Yes, it has to be well behaved. Like to take this thing out of this integration in this manner, it has to be well behaved. But in physics, we are actually doing all things about that are well behaved. So. Okay.
I think delta function is symmetry is also a definition.
Yeah, that's a definition, obviously. By definition, delta function is symmetry.
Yeah.
So when you define this way, like actually I defined, when you define this way, these two things, you already saying that delta function is symmetry because t of t prime. So when t is coincident with t prime, then it's infinity, otherwise. So there isn't anything about like asymmetry in between this.
well, if t tends to t prime minus delta and t plus delta, in that case, the both may approach to infinity, but might be different.
Sorry, say that again.
Well, okay. I think you can start and ignore my.
No. I know there's that confusion you have. So
I think it's
okay. So it's okay because of the definition of the area. Okay, so you cannot approach two different values from two different ways, yeah, right? Okay, let's get started. So actually I should clean my whiteboard again and state the problem we were talking about earlier.
It's almost to 10 p.m. so we need a break, I think.
Okay, let's have a break for 5 minutes now, not more. Okay.